Welcome or welcome back to NEET Prep Go. So in the earlier video we did group 1 elements entire revision. In this we are going to do group 2 elements, that is alkaline earth metals. So group 2 elements include beryllium, magnesium, calcium, strontium, barium and radium. Out of these, all the elements except for beryllium are called as alkaline earth metals. The first element, beryllium, differs from the rest of the members of the group and shows anomalous properties and diagonal relationship with aluminium. Just like lithium used to show diagonal relationship with magnesium. The atomic and physical properties of alkaline earth metals are shown in table 10.2. Electronic configuration, that is alkali metals had one electron after their noble gas core NS1. Now alkaline earth metals are going to have two electrons, that is NS noble core and then that is noble gas and then NS2 configuration. And just like alkali metals, these alkaline earth metals, that is their compounds are going to be predominantly ionic. Beryllium, that is 2s2, magnesium 3s2, calcium 4s2, strontium 5s2, barium 6s2, radium 7s2. Atomic and ionic radii, the atomic and ionic radii of alkaline earth metals are going to be smaller than those of alkali metals. Why? Because as we go across the group, then the nuclear charge increases, and as the nuclear charge increases, the ionic radii decreases. Therefore all the alkaline earth metals are going to have that is the corresponding alkali metals in the same period are going to have larger atomic and ionic radii than that of alkaline earth metals. Within the group, the atomic and ionic radii increase as we go down the group in the alkaline earth metals or group 2 elements because of the addition of new shells. Now ionization enthalpy, just like alkali metals, the alkaline earth metals also have considerably low ionization enthalpy, and it decreases as we go down the group as the atomic size increases with respect to nuclear charge, and the two valence electrons on the outside, they have very low metallic bonding, and they can get readily the metal alkaline metal can lose them, and therefore the ionization enthalpy it decreases as we go down the group because the screening also increases. The first ionization enthalpy of alkaline earth metals is going to be greater than that of alkali metals because alkali metals only have one valence electron, and if they lose that one valence electron, then they will attain a noble gas configuration, that is a stable configuration. Therefore they readily lose that one electron, whereas in the case of alkaline earth metals there are two electrons. Therefore the first ionization enthalpy, alkaline earth metals, greater energy you have to supply than that of alkali metals, whereas in the second ionization enthalpy is going to be much lesser of alkaline earth metals than that of alkali metals. This is because now, while removing the second electron, the alkali metals have reached the noble gas configuration or noble gas arrangement. Therefore it is going to take a lot of energy to remove that stable, that is one electron, whereas in the case of alkaline earth metals, if they lose this one electron, then they will themselves attain noble gas configuration. Therefore the second ionization and first ionization enthalpy of alkaline earth metals is greater than that of alkali metals, and second ionization enthalpy of alkali metals is greater than that of alkaline earth metals. Hydration enthalpy, again the same, as the ionic or atomic radii increases, hydration enthalpy decreases. Therefore as we go down the group, the hydration enthalpy decreases considerably, and hence highest hydration enthalpy is of beryllium, which is of the smallest size. It is greater than that of magnesium, greater than that of calcium, greater than strontium, greater than barium. Hydration enthalpies of alkaline earth metals are going to be larger than that of alkali metals because the atomic radii of alkaline earth metals is going to be smaller than that of alkali metals, and since we know that the hydration enthalpy is inversely proportional to atomic or ionic radii, therefore since atomic and ionic radii of alkaline earth metal is lesser than that of alkali metals, therefore the hydration enthalpy of alkaline earth metal is going to be greater than that of alkali metals. And compounds of alkaline earth metals therefore are more extensively hydrated than those of alkali metals. We know that in alkali metals, except for lithium, no other metal shows hydrates or forms hydrates. Lithium forms LiCl.2H2O. Why? Because it is the first element, it has the smallest size, it has the greatest hydration enthalpy, and it shows anomalous behavior as compared to all other metals. and it also shows diagonal relationship with magnesium. Therefore, magnesium and also calcium, both of them are going to form hydrates, that is MgCl2 and CaCl2. They are going to form MgCl2.6H2O and CaCl2.6H2O, whereas NaCl and KCl do not form such hydrates. So we saw that sodium, that is in the first group 1, and potassium, both of them, both of their halides did not form any hydrates, whereas in group 2 elements, MgCl2.6H2O and CaCl2.6H2O, that is both are going to form hydrates, second group elements. Now that is group 2 elements. Physical properties. Alkaline earth metals are generally silvery white, lustrous and relatively soft, but they are harder than that of alkali metals. Beryllium and magnesium appear to be somewhat grayish. Then melting and boiling point of the alkaline earth metals is going to be greater than alkali metals. Why? Because of their smaller size, and the trend is however not systematic. Because of the low ionization enthalpies, the alkaline earth metals are strongly electropositive in nature. So most electropositive is obviously going to be group 1 elements, but due to their due to the low ionization enthalpies of alkaline earth metals, they are strongly electropositive in nature, and the electropositive nature, just like in alkali metals, it increases as we go down the group from beryllium to barium. Calcium, strontium and barium impart characteristic brick red, crimson and apple green colors respectively to the flame. So calcium imparts brick red color, strontium imparts crimson color, and barium imparts apple red color to the flame. In flame, the electrons are excited to higher energy level, and when they come back to the ground state, then they emit energy in the form of visible light. The electrons in beryllium and magnesium are too strongly bound to get excited by the flame. So in beryllium and magnesium, this is the exception, in beryllium and magnesium, the electrons are too strongly bound to get excited by the flame. Hence these elements do not impart any color to the flame. So only calcium, strontium, barium impart that is color to the flame. That is, flame test can be seen by flame photometry and atomic spectroscopy, and that is calcium gives brick red color, strontium gives crimson color, and barium gives apple green color. Magnesium and beryllium, the electrons are too strongly bound to them, and therefore they do not get excited, that is by the flame, and they do not impart any color to the flame. Now the flame test for calcium, strontium and barium is helpful in their detection and qualitative analysis and estimation by flame photometry. The alkaline earth metals, like those of alkali metals, have very high electrical and thermal conductivities, which are typical characteristics of metals. So very high thermal and electrical conductivities alkaline earth metals have, just like alkali metals, and these are typical characteristics of metals. Now we come to ionization enthalpy, that is beryllium has very high ionization enthalpy. It decreases for magnesium, then again decreases for calcium, decreases for strontium, decreases for barium, but radium has greater ionization enthalpy than barium. Similarly, this is for the first ionization enthalpy. Then second ionization enthalpy also same, it decreases, but again radium has greater first as well as second ionization enthalpy as compared to barium. Then hydration enthalpy, it considerably decreases as we go down the group because the atomic and ionic radii increases, and metallic radii increases as we go down the group. Ionic radii also increases as we go down the group. Now melting point, boiling point, it is not going to be uniform. Melting point and boiling point, both of them should increase as we go down the group. So for beryllium it is very high, but for magnesium it is low. So magnesium has a lower melting point and boiling point than beryllium. Then calcium and for calcium, the melting and boiling point both are higher than that of magnesium. Then the melting point of strontium is lesser than calcium. Then barium is even lesser and radium is the smallest. Strontium, then strontium's boiling point is lesser than calcium, but barium has a greater boiling point than strontium, and radium also has a greater boiling point than strontium, but lesser than barium. Now density. Beryllium has a higher density, magnesium has lower density than that of beryllium, calcium has lower density than that of magnesium, but strontium has highest density than beryllium, magnesium and calcium. Then barium has even more density, radium has even more density. Melting and boiling point decrease as we go down the group, but in this case it is completely and density increases as we go down the group, but for beryllium, magnesium and calcium it is it is different. Standard electron potential occurrence in atmosphere, parts per million. Now let's come to chemical properties. The alkaline earth metals are less reactive than that of alkaline metal, and the reactivity also increases as we go down the group. So for alkaline metals also the reactivity used to increase as we go down the group. For alkaline earth metals also reactivity increases as we go down the group, but they are going to be less reactive than alkali metals. Now, reactivity towards air and water. Beryllium and magnesium are kinetically inert to oxygen and water because of the formation of an oxide film on their surface. So beryllium and magnesium are kinetically inert to oxygen and water because of the formation of an oxide film on their surface. However, powdered beryllium burns brilliantly on ignition in air to give beryllium oxide BeO and beryllium nitride Be3N2. Magnesium is more electropositive. So the magnesium powder also burns with dazzling brilliance in air to give magnesium oxide MgO and magnesium nitride Mg3N2. Calcium, strontium and barium are readily attacked by air to form oxide and nitride. They also react with water with increasing vigor even in cold to form hydroxides. So beryllium and magnesium are kinetically inert to oxygen and water because of the formation of an oxide film on their surface. But if you burn powdered beryllium and powdered magnesium, then beryllium will form BeO, beryllium oxide, and beryllium nitride Be3N2. Magnesium is more electropositive and it will burn with a dazzling flame in the air to give again magnesium oxide and magnesium nitride. Then calcium, strontium and barium, all three of them readily get attacked by air to form oxide and nitride. They also react with water with increasing vigor even in the cold. That is, even with cold water they can react to form hydroxides. Then reactivity towards halogen, all alkaline earth metals combine with halogen at elevated temperatures to form halides. That is M plus X2 gives Mx2, and whereas in that case it was M plus X minus. Over here it is Mx2. where X can be fluorine, chlorine, bromine, iodine. Thermal decomposition of NH4 whole twice BeF4 is the best route for the preparation of beryllium fluoride, and beryllium fluoride is conveniently made from the oxide. So how is beryllium chloride made? Beryllium chloride is made from beryllium oxide, that is the oxide of beryllium, and thermal decomposition of ammoniated beryllium fluoride is the best route for the preparation of beryllium fluoride. Now reactivity towards hydrogen, all the elements except beryllium combine with hydrogen upon heating to form their hydrides. That is MH2. But BH2, however, can be prepared by the reaction of BeCl2 with LiAlH4. So reactivity towards hydrogen, all the elements except for beryllium combine with hydrogen upon heating to form their hydrides MH2, but BeH2 however can be prepared by the reaction of beryllium chloride with LiAlH4, which is a reducing agent. So BeCl2 plus LiAlH4 give you BeH2. Then reactivity towards acid, the alkaline earth metals react readily with acids, liberating dihydrogen. Now reducing nature, like alkaline metals, alkaline earth metals are strong reducing agent. This is indicated by large negative values of their reduction potential. However, their reducing power is less than those of their corresponding alkaline metals. So that is in that period their reducing power is going to be less than their corresponding alkaline metals. Beryllium has less negative value compared to other alkaline earth metals. However, its reducing nature is due to large hydration energy associated with the small size of beryllium ion and relatively large value of atomization enthalpy of the metal. So it has beryllium has less negative value compared to other alkaline earth metals, but its reducing nature is due to its large hydration energy, which is associated with the small size of beryllium ion, as well as relatively large value of the atomization enthalpy of beryllium metal. Then solutions in liquid ammonia, like alkaline metals, the alkaline earth metals also dissolve in liquid ammonia. In that case, we used to get deep blue solution. In this case, we get deep blue-black solution. Deep blue-black solution forming ammoniated electron, same M plus X plus Y NH3 gives MNH3X plus 2 NH3Y. From these solutions, the ammoniates can be recovered. Uses. Beryllium is used in the manufacture of alloys. Again, this entire part have to remember. Beryllium is used in the manufacture of alloys. Copper beryllium alloys are used in the preparation of high strength springs. Metallic beryllium is used for making windows of X-ray tubes. Magnesium forms alloy with aluminium, zinc, manganese and tin. Okay, so firstly, beryllium is used for the manufacture of alloys. Copper beryllium alloys are used in the preparation of high strength springs. Where is beryllium used? That is, beryllium is firstly used in the manufacture of alloys, and copper beryllium alloys are used in the preparation of high strength springs. Metallic beryllium is used for making windows of X-ray tubes. Metallic beryllium is used for making windows of X-ray tubes. Then magnesium forms alloys with aluminium, zinc, manganese and tin. Magnesium aluminium alloys help in making aircraft used in being light in mass are used in aircraft construction. Then magnesium powder and ribbon is used in flash powders, bulb, incendiary bomb and signal. A suspension of magnesium hydroxide in water is called as milk of magnesia, and it is used as an antacid in medicine. Then magnesium carbonate is an ingredient of toothpaste. Calcium is used in the extraction of metals from oxides which are difficult to reduce with carbon. Where and why is calcium used? It is used in the extraction of metals from oxides which are difficult to reduce with carbon. Calcium is used in the extraction of metals from oxides which are difficult to reduce with carbon. Calcium and barium metals, owing to their reactivity with oxygen and nitrogen at elevated temperatures, have been often used to remove air from vacuum tubes. Radium salts are used in radiotherapy, for example, in the treatment of cancer. So what are the uses? That is, beryllium is firstly used in the manufacture of alloys. Copper beryllium alloys are used in the preparation of high strength springs. Then metallic beryllium is used for making windows of X-ray tubes. Then magnesium forms alloys with aluminium, zinc, copper, tin, manganese. Magnesium aluminium alloys, being light and mass, are used in aircraft construction. Then magnesium powder and ribbon is used in bulbs, incendiary bombs, flash powders and signals. A suspension of magnesium hydroxide in water is called as milk of magnesia, and it is used as an antacid and medicine. Magnesium carbonate is an ingredient of toothpaste. Calcium is used in the extraction of metals from oxides which are difficult to reduce with carbon. Calcium and barium metals, owing to their very high reactivity in oxygen and nitrogen at elevated temperatures, are used to remove air from vacuum tubes. Radium salts are used in radiotherapy, for example, to treat cancer. X-ray tubes. Beryllium, manufacture of alloys. Copper beryllium alloy, high strength spring. Metallic beryllium, making windows of X-ray tube. Magnesium aluminium, that is aircraft construction. Magnesium powder and ribbon, flash powder, bulb, incendiary bomb, signal. Magnesium hydroxide in water, milk of magnesia, antacid. Magnesium carbonate, toothpaste. Then radiotherapy in cancer, calcium, barium metals to remove air from vacuum tubes, calcium used to extract metals from their oxides, the ones that carbon cannot reduce. Now, general characteristic of compounds of the alkaline earth metals. The depositive oxidation state M2 plus is the predominant valence of group 2 element. So M, in that case, the monovalent M1 plus, here M2 plus. Dipositive oxidation state. The alkaline earth metals form compounds which are predominantly ionic but less ionic than that of alkali metals. Why? Because they have only one electron, right, which they readily lose, and which keeps getting that is easily absorbs energy and emits and also this is due to increased and larger size, also atomic size, lesser nuclear charge, whereas in this case increased nuclear charge and smaller size, therefore they are less ionic than that of alkali metals, less electropositive than that of alkali metals. Oxides and other compounds of beryllium and magnesium are more covalent. The oxides and other compounds of beryllium and magnesium are more covalent than those formed by heavier and large size members, calcium, strontium, barium. This is also important, that is the oxides and other compounds of beryllium and magnesium are more covalent than those of their other members, which are heavier and larger. For example, calcium, strontium, barium. Oxides and hydroxides. The alkaline earth metals burn in oxygen to form monooxide MO. So in that case only lithium used to form monooxide Li2O, rest all used to form peroxide and superoxide. In this case, that is the alkaline earth metals burn in oxygen to form monooxide, which except for beryllium oxide have a rock salt structure. So all the monooxides of alkaline earth metals have rock salt structure except for beryllium oxide. Beryllium oxide is essentially covalent in nature. Beryllium oxide is essentially covalent in nature. The enthalpies of formation of these oxides are quite high, and consequently they are very stable to heat. While oxides of other elements are ionic in nature, all these oxides except for beryllium oxide are basic in nature and react with water to form sparingly soluble hydroxides. So oxides and hydroxides, that is alkaline metals, burn easily, that is in oxygen to form monooxide, and all monooxides MO except for beryllium oxide BeO have a rock salt structure. Beryllium oxide is essentially covalent in nature. The enthalpies of formation of these oxides are quite high and very stable to heat. Beryllium oxide is amphoteric. Rest all oxides of group 2 elements or alkaline metals are ionic and basic in nature, and they react with water to form sparingly soluble hydroxides. So except for beryllium oxide, that is, you can see all other oxides MO when reacted with H2O water will give us sparingly soluble hydroxides MOH whole twice. Solubility, thermal stability and basic character of these hydroxides. Uh, yeah, so the solubility, thermal stability and basic character of these hydroxides increase with the increasing atomic numbers from magnesium hydroxide to barium hydroxide. Solubility, thermal stability and basic character increases from magnesium hydroxide to barium hydroxide. The alkaline earth metals hydroxides are however less basic and less stable than alkali metal hydroxides. Beryllium hydroxide is amphoteric in nature. Why? Because of its covalent nature, small size, and it does not form rock salt structure. And beryllium hydroxide is amphoteric in nature. It reacts with acid and alkali both. That's why you call that amphoteric. Beryllium hydroxide plus 2 that is OH minus gives berylate ion. Halides. Except for beryllium halide, all other halides of alkaline earth metals are ionic in nature. Beryllium halides are covalent in nature and they are soluble in organic solvents. Beryllium chloride has a chain structure in the solid state as shown below. In the vapor phase, beryllium chloride tends to form a chloro-bridge dimer which dissociates into the linear monomer at high temperatures. In the vapor phase, beryllium chloride tends to form a chloro-bridge dimer which associates into linear monomer at high temperatures. So BeCl2 essentially in the vapor phase it forms a chloro-bridge dimer, but it dissociates to form a linear monomer at high temperatures, that is 1200 Kelvin. The tendency to form halide hydrates gradually decreases. For example, MgCl2.6H8H2O, CaCl2.6H2O, SrCl2.6H2O, and BaCl2.2H2O down the group. So gradually the tendency to form hydrates, that is halide hydrates, it decreases as we go down the group. Dehydration of hydrated chloride, bromide, and iodide of calcium, strontium, and barium can be achieved on heating. However, for beryllium and magnesium, on heating, they suffer hydrolysis. The fluorides are relatively less soluble than the chlorides owing to their high lattice energies. Fluorides are less soluble than the chlorides. Why? Because of their higher lattice energies. Now, salts of oxoacid, alkaline earth metals also form salts of oxoacid such as carbonate, sulfate, nitrate. Carbonates of alkaline earth metals are insoluble in water and they can be precipitated by the addition of sodium or ammonium carbonate solution to a solution of soluble salt of these metals. So carbonates of alkaline earth metals, they are all insoluble in water. And how can you precipitate the carbonate of alkaline earth metals which are insoluble in water? By the addition of sodium or ammonium carbonate solution to a solution of carbonate, alkaline earth metal carbonate and water, that is soluble salt of these metals. The solubility of carbonates in water decreases as the atomic number of the metal ion increases. So as we go down the group, the solubility will decrease. All the carbonates decompose on heating to give carbon dioxide and oxide. All the carbonates, that is MCO3, they decompose to give carbon dioxide and oxide, MO. Beryllium carbonate is unstable and it can be kept only in the atmosphere of carbon dioxide. The thermal stability increases with increasing cationic size. So as we go down the group, the thermal stability increases, but the water solubility decreases. Sulfate of alkaline earth metals of all white solids are all white solids. Sulfates of all the alkaline metals are all white solids and they are all stable to heat. Beryllium sulfate and magnesium sulfate are readily soluble in water. Beryllium sulfate and magnesium sulfate are readily soluble in water, but the solubility decreases from calcium to barium. The greater hydration enthalpy of beryllium and magnesium ions overcome the lattice enthalpy factor and therefore their sulfates are soluble in water. But when you come to nitrates, nitrates are made by dissolution of carbonates in dilute nitric acid. So when the carbonates are dissolved, that is dissolution takes place of the carbonates in dilute nitric acid HNO3, then nitrates are formed. Magnesium nitrate crystallizes with 6 molecules of water, whereas barium nitrate crystallizes as the anhydrous salt. This again shows a decreasing tendency to form hydrates as we go from magnesium to barium with increasing size and decreasing hydration enthalpy. All of them decompose to give the oxide like lithium nitrate. They all give oxide and nitrogen dioxide and oxygen. Why does the solubility of alkaline earth metal hydroxides increase down the group? That is the anion being common, the cationic radius will influence the lattice enthalpy. Since lattice enthalpy decreases much more than the hydration enthalpy with increasing ionic size, solubility increases as we go down the group. Why does metal carbonates and sulfates solubility in water decrease as we go down the group? This is because the size of anions being much larger to that of cations, lattice enthalpy remains almost constant within a particular group and hydration enthalpy decreases down the group, therefore solubility in water also decreases down the group for alkali metal carbonates and the sulfates. So solubility, that is Water solubility for carbonate and sulfate decreases as we go down the group, but for hydroxides it increases. Anomalous behavior of beryllium. Beryllium is the first member of group 2 metals. It shows anomalous behavior as compared to all other members of its groups. Further, it shows diagonal relationship to aluminium. Beryllium has exceptionally small atomic and ionic size, and thus it does not compare well with other members of the group. Beryllium has exceptionally small atomic and ionic size, and because of beryllium's exceptionally small atomic and ionic size, it does not compare well with the other members of the group. Because of high ionization enthalpy and small size, it forms compounds which are largely covalent and get easily hydrolyzed. Beryllium does not exhibit coordination number more than 4. Beryllium does not exhibit coordination numbers more than 4. As in its valence there are only 4 orbitals. The remaining members of the group having a coordination number of 6 make use of the d orbitals. Oxide and hydroxide of beryllium, unlike hydroxides of other elements in the group, are amphoteric in nature. So oxides and hydroxides of beryllium, unlike other hydroxides which are basic in nature, for beryllium they are amphoteric in nature. Diagonal relationship between beryllium and aluminium, that is ionic radius of beryllium, is estimated to be 31 picometers, and the charge by radius ratio of aluminium is nearly same. What are the ways in which beryllium and aluminium are similar? That is, beryllium is not readily attacked by acids because of the presence of oxide film on the surface of the metal. For aluminium also it is the same, that is, aluminium oxide is formed Al2O3, which prevents from aluminium by getting attacked by acids readily. Then beryllium hydroxide dissolves the excess of alkali to give berylate ion. So beryllium hydroxide dissolves the excess of alkali to give a berylate ion, just like ammonium hydroxide gives aluminate ion. The chlorides of both beryllium and aluminium have chlorine-bridge chloride structure in vapor phase. Both the chlorides are soluble in organic solvent, and both of them are therefore strong Lewis acids. They are used as Friedel-Crafts catalysts. Beryllium and aluminium ions have strong tendency to form complexes. Some important compounds of calcium are calcium oxide, calcium hydroxide, calcium sulfate, calcium carbonate, and cement. They are industrially important compounds, and the large-scale preparation of these compounds and their uses are described below. Firstly, calcium oxide, also called as calcium, the CaO, quicklime. Calcium oxide is also called as quicklime. It is prepared on a commercial scale by heating limestone, which is calcium carbonate, in a rotary kiln at 1070 to 1270 Kelvin. When you heat limestone or calcium carbonate in a rotary kiln, then you get quicklime or calcium oxide and carbon dioxide. Carbon dioxide is removed as soon as it is produced to enable the reaction to proceed to completion. Otherwise, it won't proceed to completion. Then calcium oxide will come back and react. So calcium oxide is a white amorphous solid. It has a melting point of 2870 Kelvin. On exposure to atmosphere, it absorbs moisture and carbon dioxide. Calcium oxide and water will give us calcium hydroxide, and calcium oxide and carbon dioxide will give us calcium carbonate. The addition of limited amount of water breaks the lump of lime. This process is called as slaking of lime. Quicklime slaked with soda gives us soda lime. Calcium oxide plus water gives us calcium hydroxide, that is slaked lime or calcium hydroxide, and calcium oxide reacted with carbon dioxide gives us CaCO3, that is limestone or calcium carbonate. The addition of limited amount of water breaks the lump of lime. This process is called as slaking of lime. Quicklime slaked with soda gives us soda lime. Being a basic oxide, it combines with acetic oxides at high temperature such as silicon oxide to form SiO3 and P4 O10 to give 2Ca3PO4 whole twice. Calcium phosphate. It is an important primary material for manufacturing cement, and it is also the cheapest form of alkali. Calcium oxide, calcium hydroxide, or calcium oxide or quicklime is an important primary metal for the manufacture of cement, and it is cheapest form of alkali. It is used in the manufacture of sodium carbonate from caustic soda. Calcium oxide is used for the manufacture of sodium carbonate Na2CO3 from caustic soda NaOH. Then it is employed in the purification of sugar in the manufacture of dye stuff. Then calcium hydroxide or slate lime, it is prepared by adding water to quicklime or CaO. It is white amorphous powder. It is sparingly soluble in water. It is not soluble in water. Aqueous solution is called as lime water, and a suspension of slate lime in water is called as milk of lime. A suspension of slate lime in water, calcium hydroxide in water is suspended is called as milk of lime, and aqueous solution of calcium hydroxide is called as lime water. When carbon dioxide is passed through lime water, then it turns milky due to the formation of calcium carbonate. On passing excess of carbon dioxide, the precipitate dissolves to form calcium hydrogen carbonate. So if you pass carbon dioxide, then the solution will turn milky and form calcium carbonate. But if you pass excess of carbon dioxide, then that is the calcium carbonate formed will in turn change into calcium hydrogen carbonate. Milk of lime, that is calcium hydroxide suspended in water, reacts with chlorine to form hypochlorite, which is a constituent of bleaching powder. Calcium hydroxide, that is milk of lime, with chlorine forms hypochlorite, a constituent of bleaching powder. That is CaCl2 plus CaOCl2 whole twice together gives us bleaching powder. Uses, that is it is used in the preparation of mortar, which is a building material. That is calcium hydroxide is used, or slate lime is used in the building of mortar, in manufacture of mortar or making mortar, which is a building material. It is used in whitewash due to its disinfectant nature. It is used in glass making, tanning industry for the preparation of bleaching powder and purification of sugar. Calcium carbonate occurs in nature in several forms such as limestone, chalk, marble, etc. It can be prepared by passing carbon dioxide through slate lime or by addition of sodium carbonate to calcium carbonate. So calcium chloride. So calcium carbonate CaCO3, also called as limestone, chalk, marble. It has several forms. It can be prepared by passing carbon dioxide through slate lime, that is calcium hydroxide, or by the addition of sodium carbonate, that is washing anhydrous sodium carbonate Na2CO3 to calcium chloride CaCl2. Excess of carbon dioxide should be avoided since this leads to the formation of water soluble calcium hydrogen carbonate. That is, excess of carbon dioxide should be avoided since this leads to the formation of calcium hydrogen carbonate. Calcium carbonate is white fluffy powder. It is almost insoluble in water. When heated to 1200 Kelvin, it decomposes to form carbon dioxide. So calcium carbonate, when heated at 1200 Kelvin, it decomposes to form carbon dioxide and quicklime calcium oxide. It reacts with dilute acid to form carbon dioxide. That is, with dilute acid HCl H2SO4, it forms carbon dioxide, water, and calcium chloride, calcium sulfate, that is salt. Then uses, it is used as a building material in the form of marble and in the manufacture of quicklime, that is calcium oxide. Then it is used along with magnesium carbonate. It is used as a flux in the extraction of metals such as iron. Especially precipitated calcium carbonate is extensively used in the manufacture of high quality paper, and it is used as an antacid, mild abrasive toothpaste, and constituent of chewing gum, filler in cosmetics. So calcium carbonate has many uses, that is building material in the form of marble, limestone, etc. It is used in manufacture of quicklime. It is used as a filler in cosmetics. It is the constituent of chewing gum. It is the constituent of that is mild abrasive toothpaste. It is also used as an antacid. It is used in the manufacture of high quality paper, and along with calcium carbonate along with magnesium carbonate is used as a flux in the extraction of metals such as iron. Calcium sulfate is called as plaster of Paris, that is CaSO4. dot half H2O. It is hemihydrate, half H2O, hemihydrate of calcium sulfate, and it is obtained when gypsum, which is CaSO4.2H2O, is heated to 393 Kelvin. So when calcium sulfate CaSO4.2H2O is heated to 393 Kelvin, then we get above 393 Kelvin, no water crystallization is left, and we get anhydrous calcium sulfate. And at 393 Kelvin, we get CaSO4.half H2O from gypsum, that is hemihydrate, we are also called as plaster of Paris, and anhydrous calcium sulfate is called as dead bond plaster. It has a remarkable property of setting with water. On mixing with an adequate quantity of water, it forms plastic mass that gets into hard solid in 5 to 15 minutes. That is, plaster of Paris has a remarkable property of setting with water, and on mixing with adequate quantity of water, it forms a plastic mass which gets into a hard solid in 5 to 15 minutes. Largest use of plaster of Paris is obviously in the building industry as well as plasters. It is used for immobilizing the affected parts of organ where there is a bone fracture or a sprain. It is also employed in dentistry, in ornamental work, and making cast and statue and busts. Then cement is an important building material. It was first introduced in England in 1824 by Joseph Aspdin. Cement is an important building material. It was first introduced in England in 1824 by Joseph Aspdin. It is also called as Portland cement. Why is it called as Portland cement? Because it resembles with the natural limestone quarried in the Isle of Portland, England. It is called as Portland cement because it resembles with the natural limestone which was quarried in the island of Portland in England. Cement is a product obtained by combining a material rich in lime, that is calcium oxide, with other materials such as clay, which contains silicon oxide, along with the oxides of aluminium, iron, and magnesium. The average composition of Portland cement. What is the average composition of Portland cement? It is 50 to 60% of your quicklime calcium oxide. Then your silica content, that is silicon SiO2, 20 to 25%. Then all other oxides, that is oxide of aluminium, Al2O3, 5 to 10%, magnesium oxide 2 to 3%, iron oxide Fe2O3, 1 to 2%, and SO3, that is sulfur trioxide, 1 to 2% for good quality of cement. The ratio of silica SiO2 to Al2O3 should be between 2.5 and 4, and ratio of calcium oxide, that is lime, to the total oxides of silicon, aluminium, and Fe2O3 should be as close as possible to 2. So for a good quality of cement, that is the ratio of silica to alumina. Silica to alumina should be 2.5 and 4, should be between 2.5 and 4, and the ratio of lime to the total oxides of all silicon, aluminium, and iron should be as close as possible to 2. Raw materials for manufacture of cement are limestone and clay. What are the raw materials for manufacture of cement? Limestone and clay, because you saw, right, CaO and when clay and lime are strongly heated together, they fuse and react to form a cement clinker. This clinker, when mixed with 2 to 3% by weight of gypsum, that is CaSO4.2H2O, forms cement. Thus, important ingredients present in Portland cement are dicalcium silica, Ca2Si4, 26%, tricalcium silicate, Ca3SiO5, 51%, and tricalcium aluminate, 11%. What are the most important ingredients present in Portland cement? Dicalcium silicate, that is Ca2SiO4, 26%, then tricalcium silicate, Ca3SiO5, 51%, and tricalcium aluminate, Ca3Al2O6, 11%. Setting of cement. When mixed with water, the setting of cement takes place to give a hard mass. This is due to hydration of the molecules of the constituents and their rearrangement. Setting of cement. When the cement is mixed with water, then setting of cement takes place to give us a very hard mass. Why is this? This is due to the hydration of molecules of the constituents and their rearrangement. The purpose of adding gypsum is to slow down the process of setting of cement so that it gets sufficiently hardened. So when you mix the water with cement, then setting takes place to give a hard mass. Why does this happen? This is because of hydration of molecules of the constituents and their rearrangement. The purpose of adding gypsum is to slow down this process so that it gets sufficiently hardened. Cement has become a commodity and national necessity for any country next to iron and steel, and it is used in concrete and reinforced concrete, in plastering and construction of building, bridges, dams, etc. Biological importance of magnesium and calcium. Adult body contains 25 gram of magnesium and 1200 gram of calcium compared with only 5 gram of iron and 0.06 gram of copper. Daily requirement has been estimated 200 to 300 milligrams. Then all the enzymes that utilize ATP and phosphate transfer. All the enzymes that utilize ATP in phosphate transfer require magnesium as a cofactor. So all the enzymes which utilize ATP in phosphate transfer, all the enzymes which utilize ATP in phosphate transfer require magnesium as a cofactor. The main pigment for the absorption of light in plants in chlorophyll, which contains magnesium, it's chlorophyll, and it contains magnesium. About 99% of body calcium is present in your bones and teeth. It also plays important role in neuromuscular function, interneural transmission, cell membrane integrity, and blood coagulation. Calcium concentration in plasma is regulated at about 100 milligram per liter. It is maintained by two hormones, that is calcitonin and parathyroid hormone. Do you know that bone is not an inert and unchanging substance, but it is continuously being solubilized and redeposited to the extent of 400 milligrams per day in man. All this calcium passes through the plasma. So it is not, bone is not inert and unchanging. It is continuously being solubilized and redeposited to the extent of 400 milligrams per day in man. All this calcium passes through the plasma. So one important point is ATP in phosphate transfer requires magnesium as a cofactor. ATP in phosphate factor requires magnesium as a cofactor, and magnesium, that is chlorophyll in plants, that is for the main pigment for absorption of light, is chlorophyll, and it contains magnesium. 99% of the body calcium is present in bones and teeth, and calcium has other important roles in neuromuscular function. That is due to calcium that excitation takes place, interneural transmission, then cell membrane integrity and blood coagulation. Calcium concentration in plasma is regulated about 100 milligrams per liter. It is maintained by two hormones, calcitonin and parathyroid hormone. Calcium is maintained by two hormones. What are those two hormones? Calcitonin and parathyroid hormone. And it is not inert, it keeps changing, that is, it is solubilized and redeposited in 400 milligrams per day in man. And where does all this calcium pass through? Through the plasma. Thank you.